So plasma arc machining. Okay. So this is one of the thermal machining process. There are many thermal machining process like electron beam machining (EBM), laser beam machining (LBM), and plasma arc machining or PAM, shortly called as PAM, is one of the thermal machining process. These are used for machining different types of workpiece of different material. So it is also one of the thermal machining process. Okay, in this process, the gases are heated and charged to plasma state. In laser beam machining, the source or the state at which the source is laser. Similarly, as the name indicates, plasma. Okay, it has a plasma arc machining. We are using plasma to machining. The thermal machining process is done by plasma. So as you can see, there is a gas mixture supply over here. So this is a whole apparatus, and there's a gas mixture supply through here. And this one is an electrode. Okay, this is an electrode, and there's a gas mixture supply or the one of the vent of the apparatus, and we have a chamber inside. So this electrode is connected by a power supply, and the negative terminal is connected to electrode, and positive terminal is connected to workpiece. So as you can see, that will be in a closed circuit. Okay, so the gas mixture supplied in this part, and the electrons from the electrode, they together mix to form the plasma. Okay, that's how the plasma formed from the gas mixture, the gas ions, and the electron ion from the electrode, they took the react to form plasma. And the plasma state that form here is superheated and is electrically ionized. Okay, so electrically ionized because we are supplying a DC power supply to the electrode. The plasma state is superheated and electrically ionized gases at approximately 5000 degrees Celsius. The plasma that formed out here will be having a temperature range of 5000 degrees Celsius. Okay, uh, as you can see, this another figure of the plasma arc machining. As you can see, we have a nozzle down here. This is a workpiece, the molten material. This is the workpiece, and yeah, the cutting gas is applied, and there's electrode. Electrode is connected to an power supply, DC power supply, and the cutting gas along with the electrode to the form the plasma. Okay, that's how the plasma is created at the plasma arc machining. We are creating plasma, and this plasma is used for machining, thermal machining process. The high velocity jet flow of the hot ionized gas melts the metal and then removes the molten material to form a curve. So there will be high velocity jet flow. So you can see that this plasma will be having a very high velocity. Okay, the high velocity of jet flow of the hot ionized gas. This gas supply on the other end will be having a very high velocity, which with the ions in the electrons from the electrode to the from plasma, right? So the gas supplied will be having a very high velocity. So the plasma that that's done machining on the workpiece, that will form curve. Curve is simply the removed remaining removed part is called curve. Okay, if you are machining an workpiece and suppose there is a hole or a part of it is removed, as you can see, the remaining part, the whole part can be called as a curve. Okay, so high velocity jet is applied. This continuous high velocity jet is applied. So the previously machined molten metal is removed by this high velocity jet. Okay, that's what this point saying. The metal usually cut with this process are aluminum and stainless steel. So workpiece that will be used for plasma arc machining are usually aluminum and the stainless steel. The most commonly aluminum and stainless steel are used, and pots can also be used for cutting carbon steel, copper alloys, and nickel. So further, not only aluminum stainless steel, but it can also use for cutting carbon steel, copper alloys, and nickel alloys. The metal removal in PM is basically due to high temperature produced, right? This plasma that produce from the gases and electrode is very much high temperature. We already mentioned this 5000 degrees Celsius. So basic working is due to the very high temperature produced by the plasma. The heating of the workpiece is as a result of anode heating due to direct electron bombardment plus convection heating from the high temperature plasma that accompanies the arc, right? So the heating, of course, is a thermomeasuring process due to the high temperature of the plasma. So this due to the anode heating. So from the anode heating, Because why it is called anode heating? Because as you can see from the circuit, this workpiece is the anode part, and this electrode is a cathode part. So obviously this is a anode. So it is the anode is getting heated, right? So the heating of the workpiece is as a result of anode heating due to direct electron bombardment. Okay, the electrons are bombarded. The plasma, high plasma electrons are bombarded due to the very high velocity and high temperature plasma that accompanies it. Okay, so the heat produced is sufficient to raise the workpiece temperature above its melting point, and high velocity gas stream effectively blows the molten metal away. Of course, the temperature I am supplying should overcome the melting point of the workpiece. Then only the thermal machining process occur, and the molten state is formed. And the molten state formed, or the molten metal formed, is removed by the high velocity, what do you call a high velocity jet from the gas supply. So this actually it is machining, and the removal is done in the same process. That's a specialty of plasma arc machining. There are two types of plasma arc machining: transferred plasma arc machining and non-transferred plasma arc machining. So in transferred plasma arc machining, this is the figure of transferred plasma arc machining. Just like the wrong figure, we have electrode, there's a nozzle and plasma gas. Look at the gas supply. You can see the plasma is formed there. There is a workpiece. So major difference, the plasma jet can be operated in the transferred mode where the electric current flows between the plasma torch electrode and the workpiece. So there's a continuous supply of okay, so current and flows between the plasma torch electrode. Okay, so the plasma torch electrode is a negative terminal of the power supply. So it is a cathode, and workpiece is a anode. Okay, so there will be in complete circuit electric current is flow through this circuit is completed by the from the plasma torch. So you can see the workpiece is connected to the anode. So obviously this will be a complete circuit. Transfer system. Okay, in transferred plasma system, the whole circuit, the arc is complete. This arc is complete by making contact to the workpiece, right? As you can see, the circuit is complete because the anode is connected to the workpiece. So the arc is completed by making contact with the workpiece. The arc is completed making the contact with the workpiece. That's an important point of transferred plasma arc machining. Okay, the remaining all the working principle of is same as the general plasma arc machining. Transferred plasma arc machining, or the workpiece is the whole circuit is arc, or the arc is completed by contact to the workpiece. And in non-transferred plasma machine, as you can see, the power supply is completed with a nozzle. Okay, not on the workpiece. The whole arc circuit is completed with a nozzle. Okay, a plasma jet can be operated in the non-transferred mode, where the electric current is flows between the electrode and torch nozzle. Okay, the electric current is flowing between the obviously there will be electrode, torch, and nozzle. Okay, here the this flowing between the plasma torch, electrode torch, and workpiece in transfer plasma machining. But in non-transfer machining, it is between the electrode is same between nozzle. That's the difference between transferred and non-transferred plasma machining. And non-transferred arc extend from the electrode or cathode to the end of the nozzle. Right. The nozzle acts as the anode. Here, nozzle acts as the anode. In the previous case, the workpiece acts as the anode. Here, the non-transferred plasma machining, but nozzle acts as the anode. And this type of plasma jet is completely independent of the workpiece. As you can see, it's not connected to the workpiece. The power supply DC, the power supply that is supplying is not connected to the workpiece. So this does not depend. The non-transferred plasma machine does not depend on the workpiece. Okay, and so an arc is completed by contact with the nozzle. These are the major difference between the transferred plasma arc machining and non-transferred plasma arc machine. So let's discuss the process parameters. What are the parameters that affect influence the plasma arc machining? Obviously, current and intensity. Okay, intensity of supply. That the DC power supply obviously depends on the intensity of the plasma, or the heat at which it is used to machining. The plasma arc voltage, then the properties of the workpiece, the workpiece that I am using. I mean, it's melting point, what temperature it melts. So obviously depends on the machining, right? So the properties of the workpiece is one of the factor. Thickness of the workpiece, okay, whether it is how much having larger thickness or smaller. Okay, the gases which are used along with the electrode to form plasma, the gases you are using, the flow rate of the gases supply. Okay, as you have mentioned, the jet velocity, sort of the flow rate is one of the influential factors. So, flow rate of the gases is also one of the parameter. Then the working speed, the speed at which the whole machining process takes place. Then the nozzle diameter. Okay, obviously it depends on the velocity of the jet. Right? So, nozzle diameter determines the power density in the flame. If it is having a very small diameter, obviously it will be having a very high plasma power density. So, it could machine with a very high intensity on the workpiece. And then standoff distance. Standoff distance means the distance between the nozzle and the workpiece. So that's small distance between the workpiece and nozzle is what standoff distance. And these are the parameters, process parameters in plasma arc machining. Okay. Up next, the material removal rate. Obviously, this machining process, the materials are removed in a very larger rate, and because it's a therm machining process, so metal removal takes place in a very large quantity. So, metal removal rate increases with the current, but depends on the cutting speed. Okay, and the gas flow rate, thickness of the work. So, these are different factors that influence the metal removal rate. It is directly proportional to the current supply, or what ambience the current is for machining, and it also depends on the cutting speed and other factors are also gas flow rate, thickness of the workpiece. Okay, and these are the supply of the current range required for this metal removal rate. Okay, 800 ampere to 1000 ampere. Higher the value of cutting speed, more the volume of the material. Obviously, if you're having very high cutting speed, more material will be removed. Light. So, volume of the material removed is when it's higher. Uh, with respect to the value of the cutting speed. So cutting speed depends on the thickness of the workpiece material you are cutting in workpiece property and surface speed of the workpiece material. So these are the factor that depends on the cutting speed. If I have to use a very large cutting speed, I have to look on the properties of the workpiece I'm using, whether it is having a very small thickness or large thickness. So obviously the workpiece material property is on the cutting speed and portion of 10% hydrogen, 90% nitrogen are going to usually give a good general result. So these are the process parameters for a better metal removal rate. And an increase in plasma gas flow permit an increase in current, and this increase the power density of the flame and permit greater speed with less taper on the curve falls. Okay, there will be taper on the curve. Okay, I will explain curve next slide. So voltage depends on the ionization and gas flow. So this is all about the metal removal rate, certain factors or certain terms related to metal removal rate, how it influences metal removal rate in plasma machine. Then surface finish of the plasma machining. This is a machine surface, and this is what is called a curve. Okay, you can see this part is machine, right? So and the machining is usually in a tapered manner. You could not as a perfect simply cutting manner. So there's a tapered manner down here. This is what is called, this part is a curve. Okay, this cut part is called a curve in smart machining. And the quality of cut and dimensional accuracy produced by the plasma machining can be assessed by measuring the curve width. Okay, depends on how much curve width we are machining. So the heat effect is on the surface finish, the metal removal rate. These are all factors what determines the quality of cut and the dimensional accuracy. Okay, of a machine to workpiece in plasma machining, and the arc current and arc voltage are found to be the most significant parameter. Like the current and voltage is one of the many factors. Important factor determines the quality of the plasma. Then other factors include torch standoff, the distance between the torch and workpiece, angle to work, depth of cut. Okay, then lower value of the current and voltage obviously was found to be produce better surface finish. So the lower value of arc current and arc voltage. Okay, so and increase in thermal conductivity of the arc was observed to spoil the surface finish and increase the curve with an increase in heat effective zone. And as the thickness of the workpiece increases, when thickness increases, which the lower value of cutting speed tend to produce better cut quality. Okay, the machining process will be very much slow, but we will getting a better cut quality. These points are related to uh, how to obtain a better cut quality. Okay, so if you're using the thickness of the material is very much larger, then you should use a very low value of cutting speed to get a better much quality, and higher standard distance affect surface roughness and taper angle of the third surface. Okay, then the tolerance increases with the decrease in cutting speed. Tolerance means you'll be not having a very high perfectly cutting machine. The part will be getting. Of course, there will be a tolerance range, and it's a decrease with the cutting speed. And surface finish can achieve on the machine surface up to 5 to 75 micron. This is a range of surface finish, and a proper gas pressure is required to maintain, since lower value will result in the forming of spatter. So the gas supplied, the gas pressure at which it's supplying should be at a proper rate to have a better quality, and lower value of gas flow rate may result in double RC, which reduce the life of the consumable. So if I'm using a very lower value of gas flow rate, it would result in double RC. That means the electrode won't have be much life. It will affect the working of the electrode.